Hello world, this is Craig. In this video I'm going to go over my little utility program that I mentioned in my last video to convert binary values to decimal. This is in 8085 assembly language, and I'm sure it can be further optimized. It currently takes a little under 50 bytes of code to do this conversion on a 16-bit value. The source code is down in the description. So the utility converts a 16-bit binary number to its decimal equivalent. So for example, from our last video, if we have a 4-digit hexadecimal number like 3E7D, the program converts that to 15997 in decimal. If you aren't fluent with the double and add method of converting from binary to decimal, you may want to watch the last video to brush up on that. There's 3 steps in this utility. The first is to set up with a bit counter and to clear the registers. The program's going to receive the input in the HL pair, and it leaves the 5 nibbles of the BCD, the binary coded decimal output, in the C, D, and E registers, with C being the most significant nibble. After everything is zeroed and the bit counter is in place, the double and add loop begins. We need to process this loop once for each of the 16 bits. For convenience, the decrement is first, so the actual count needs to start at 17 in decimal. The loop is going to decrement the loop counter and see if it's 0. If it is 0, then the conversion is complete and the utility will just return. If there's more to do, the loop needs to first double the output. Doesn't matter what the bit value is at this point, the output has to be doubled, so that's done before we even look at the bit. The process of doubling BCD is not elegant in the 8085. We have to start with the least significant nibble pair, add them to themselves, and then save them again. Then double the next nibble pair, but this time we add in any carry that was generated from the lower nibble. Then we have to save those 2 BCD nibbles, double the next highest nibble, and add any carry, and so forth. And this is all BCD, so after each addition, we have to do the decimal adjust accumulator, or the DAA instruction. So it's pretty straightforward, but each of those takes 4 instructions. We have to get the value, add it to itself, adjust it, and save. And we just need to do a regular add for the first byte, and then add with the carry for the next bytes. If the utility needed to be a 32-bit input, then it would be using memory locations rather than registers for the output value, and it would have to do this just, 5 times rather than just 3. After the output value is doubled, the next step is to add the bit value to the output. To do this, the utility first needs to get the next bit, and to do that, it has to do a full 16-bit shift or rotate of the input value to the left. And the 8085 doesn't have a 16-bit rotate, so this is also a bit clumsy. And we have to use the carry as a storage cell to effectively connect the 2 8-bit registers. Now, if we want to preserve the original value in HL, rather than do a left shift, we want to do a full left rotate. Now, this isn't strictly necessary since we only need the bits as they come out of the left end. And once they've served their purpose, we could just throw them away. But preserving the bits in HL, in other words, doing a rotate rather than just a left shift where we shift in zeros on the right-hand side, preserving the bits can make for a nice little diagnostic tool, and it only costs us these 2 bytes of instructions. If it offends you, you can take those 2 bytes out. So to do this, the high byte is put into the accumulator and shifted left to place bit 15 into the carry. We only need bit 15. We don't want to resave that rotated high byte. So we don't move it back to where it was. We just throw it away, and we move the lower byte into the accumulator. And that's going to be rotated left. The old bit 15 moves out of the carry and into bit 0, and bit 7 moves out of bit 7 and into the carry. Then that byte has to be saved. The rotated byte has to be saved, and the higher byte is now loaded into the accumulator. We do a shift again, and that is going to move bit 7 into the bit 8 possession. And bit 15, which same bit we had before, it moves into the carry. Then that high byte is saved, and the program has effectively completed a 16-bit RLC on the HL pair. So that bit that was just rotated into the carry, so bit 15, it's tested. And if it is a 0, there's no need to do the add step because adding 0 just isn't going to change that number. So if it's 0, this jump if no carry simply goes back to the top and it starts the loop over again. If the bit counter decrements to 0, the conversion is completely over and the utility just returns. Otherwise, it processes the next bit like normal. But if the bit is a 1, then we have to do the add of the double and add method. So that bit needs to be added to the output value. And for each of the 3 bytes, the sequence looks the same. We have to get the value, do the addition, adjust the accumulator, and save the value. For the lowest nibble, the program explicitly adds 1, which is the bit value. And then from then on, it adds the immediate value 0 with the carry. Now, there may have been an easier way to just use a single instruction to just add the carry, but nothing immediately came to mind. So I just used the add immediate with carry and had the immediate value as 0. Now, if processing speed were more valuable than memory space, the utility could have just checked at each step to see if there even was a carry. And if there wasn't a carry, it could have immediately just jumped up and started the loop over again. But I chose to save those 6 bytes and just let it play out. After rippling that addition through all 5 nibbles of the BCD output value, the program just jumps back to the top of the loop to decrement, test the bit counter, and go from there. So that's it. That's the whole utility to convert a 16-bit value into binary coded decimal. Took 49 bytes with nothing more complicated than multi-byte rotates, doubles, and adds. So I have that little utility along with a little user interface to update the display programmed into this SDK85 Plus system. And it just operates as a single function calculator. If we type in a 4-digit hexadecimal value, it just tells us what that is in decimal. So if we type in 000A, then the value is 10. And ignore this over here. That's just the version of the monitor. 00FF is 255. FFFF is 65535. And as we did before, our favorite number from the last video is 3E7D. And that's the 15997. Okay, that's it. Likes, sharing, subscribers, and comments are always appreciated. Thanks for watching. Talk with you later. Bye-bye.